one of the primary differences between the work we did in the first semester and the work we're doing in the second semester is that the second semester focuses much more on field effects, not simply, what is the force of something 1 on something 2, but what would the force of, how does thing 1 affect space? So that, should I remove thing 2, how does thing 1 affect the space around it such that if a thing 2 was somewhere, we could find out what the force would be? Well, we deal with that using field effects. Now, when we're drawing fields, if I have a positive charge, then I'll draw a number of field lines acting away from this charge. And, how many? Oh, there's no specific amount that says, for a charge of 1 coulomb, you must use 16 lines, or whatever. We're going to be dealing with a lot of different scales. What's really important is there are enough field lines to illustrate what the heck you're trying to do. So we're not going to get any information in the number of lines. Now, when drawing fields, there are a couple of different ways to do this. The best field simulator at the PHET physics simulation set uses bolder arrows to show stronger fields. That's hard to do on a whiteboard or in a notebook. So what we'll do is typically use the length of the vector to show as a measure of the field strength at a particular point so this would represent the point charge or the electric field of a point charge through space, where, from the work we had done, in the previous chapter, the electric field for a single point charge is equal to the constant K, and again, the book uses 1 over 4 pi times another constant, epsilon naught. Right now I'm just using K because it's more compact, because mathematically it's easier to work in on the calculator, and because at the moment, until we reach Gauss's law, then we don't have really an understanding of what the heck this even means. It's just, as it is right now, a magic constant. But the electric field is given by that constant K times the charge divided by the distance from the point squared on a line radially outward. Now, if this were a negative charge, the radial field lines would be pointing radially inward, but that's okay. If this were a negative charge, this would be a negative number, and I'd get an electric field that's KQ over R squared, negative radially outward or radially inward. That's the easy part, and we're going to build the next steps from there.